Just want to stand off the screen so you can see it. Yeah. Well, I'll give you a heads up.
I think you forward to most for an app set.
Did. So the dynamic programming notes are cumulative. So I changed the link to the longer version of the notes.
Okay.
So if even though the knapsack lecture doesn't have explicit notes attached to it, if you look up the dynamic programming notes, it should have it in there. If I made a mistake, I'll check. But I vaguely recall that's what I did. If anyone has checked, I can confirm, I'll check it.
I know the day before yesterday it was not there.
Okay, I will check it. I will check it and make sure. I thought it, maybe I didn't. So it's all in here, and I just think it's a single node, and I export the cumulatively bigger version of it. So, or sometimes I break it up. Okay. All right. So let's start. So we're continuing with greedy, but also moving slightly. Well, we're doing a local search on greedy algorithms to local search. So what is local search? So as we have seen with greedy algorithms, right, it's easy to come up with heuristics. It's a little bit harder to come up with proofs that they work. Sometimes you can, sometimes you can't. Sometimes you can't even use easy counter examples. But sometimes it's not easy to do that. So, but greedy strategies are helpful because they give you a very good first way to attack the question, right? And so they're very handy because immediately you at least come up with something plausible, right? It may not be the best thing, but it's plausible. And often it can be quite decent, right? I mean, and even if it doesn't give you the exact answer, it can often give you something that's close to the exact answer. And that's often good enough. But sometimes you have to modify it a little bit. You have to sort of say, okay, I will come up with some solution, then I will make some small tweaks in the solution, just by locally looking at things that seem bad and fixing them. So it's almost like you do something, and you go and say, okay, let me tweak this here, let me tweak that here, let me tweak that here, locally, without sort of looking at rebuilding the whole solution. And you can actually do quite well. So this idea of combining some initial solution that you may get from a greedy algorithm, and then doing some local tweaking on it, is what is called local search. Local search is more general. It's just about making local improvements in your solution. So you come up with any kind of solution and make local improvements to make it better. This is a very powerful idea. I mean, in some ways, you could argue that this is everything in machine learning is based on local search, because everything in machine learning is based on now some kind of gradient descent, which is a local search procedure. So it's kind of important to understand the principles behind why things like local search are expected to work. And so we're going to use, as an example, sort of a discrete problem, and then we'll move to the more continuous setting. A discrete problem, where I'll show you how you start off with some kind of simple idea, may not work very well, and then you do something with local search, and it works better. And what's going to be cool about this is not only will I show you that something works better, I'll show you that even though it doesn't give you the exact answer, you can prove that it gets you close to the exact answer. And there's something you haven't seen unless you've heard about approximation algorithms. It's another different way of thinking. So when we first started looking at greedy algorithms, for the first time we had to think about, okay, what is optimal doing? And that's a weird thing to think about because it's a thing you don't know anything about, right? You've never had to say, okay, what is this imaginary thing that I have no clue about doing, and let me reason about mine in relation to that. That's how we prove that greedy solutions are optimal. We're going to go one step further and say, look, I know it's not optimal, but I'm going to prove that in comparison to this thing I don't fully understand and I can't see, I'm close to being. So before I was like, okay, I'm very fuzzy, I don't know where I am, oh, I found the optimal solution. Now I'm saying I'm very fuzzy, I don't know where I am, but I know the optimal solution is somewhere close by. So it's an even more crazy thing to think about. But this is very powerful because if you have to, a lot of the things I talk about have been around since the 70s, but if you have to say, what is the big thing in sort of the design of algorithms that change the way we think about algorithms, it is two things. This idea of being able to prove that you get close to the right answer, even if you don't actually get the right answer, and the ability to toss coins. And these are both things we're going to be talking about, randomization and approximation. So we're going to start with approximation here, and then we'll move on to randomization. Okay. So, as always, we'll start with the problem. The problem is a good vehicle to understand tools. And the problem is a very simple problem. And you've heard of it in many contexts, but I'll think we can think of it here. Think of it as, you have some kind of, let's say, gift-giving scenario. So you have people on one side, right? And you have gifts on the other side. Okay? Everyone, and there are as many gifts as people, and everyone has to be given a gift. Right? So you can just say, okay, we'll give the first person the first gift, the second person. Oh, but wait. The first person hates science fiction stories, and the first gift has to be a science fiction story. But they love cake, and one of the other gifts is cake. Okay, fine, won't take the science fiction cake. There's other person, oh, I like the cake too. So now so there are disagreements among them about what they like, and you have to come out and reconcile this. And since you have, economics training, you say, okay, I want to maximize the overall utility of my system. And what does that mean? Let's formalize it. So you can imagine that everyone has some kind of value they attach to every gift. So a person has a value attached to this gift, attached to this gift. And we'll think of this as some quantity Wij. For the ith person and the jth gift, what is the value? So since most normal people spell value with a W, with a V, we'll call it Bij. How about that? Value. So you have a Bij. So I give you Bij for every person and every gift. Okay? My goal is to assign gifts to people. There are as many gifts as people, so it's a one-to-one mapping. Right? So you can think of mapping as, we usually use this for what is called a permutation. So let's say there are n people and n gifts. So it's a permutation from 1 to n to 1 to n. It's just some kind of scrambling of 1 through n. Right? Any matching like that is going to be some kind of scrambling. And so now for person I, they get gift pi. That's what we're going to say. Okay, so the assignment is encoded by the permutation pi, so that the person I gets the gift pi I, right? And so we want to maximize utility. So we want to maximize the sum over all people, the value of the gift they get. But wait, what is the value of the gift they get? Well, it's Vi, and the gift they get is pi I. Okay? This is, of course, known as the maximum, max weight matching problem. Is the problem definition clear? So my input to the problem is the collection of all the VIGs. Right? And the people and the gifts themselves are sort of just symbolic. What's really important is the matrix of the VIGs. That's what I'm given. And my goal is to output a permutation such that that quantity is maximized. Right? Yeah. Okay. So as always, what are the greedy algorithms? What could a potential greedy strategy for this be? There could be many, right? So come up with a greedy strategy. Yeah, what a greedy strategy?
start with gift 1 and then choose the maximum happiness level or value level.
So find the person that becomes most happy by receiving gift 1.
Yeah.
Okay. I guess the converse could also be take a person and find the gift that makes them the most happy. Either of these. Yeah, right. So you can go either way. Right? Okay, so we'll define our first strategy. Let's call it S1 and 2 as find gift that maximizes VI, big gift J that maximizes VIJ, or find person I that maximizes VIJ. Right? Okay. Well, you know the drill now. What happens next?
Can I add something? You can't choose the same person twice though.
So maybe think of this like a loop. You go through a loop, right? For I equal to 1 to n, do this, or for j equal to 1 to n. So think of it going through loops. This is not a. What's the name of that? Like, what's that Christmas game? White elephant. White elephant. It's not a white elephant where you can sort of reject or steal someone else's. We're not like that game. That's a different game. It's a very interesting sort of game theory question around it as well. But we won't get into that. But if you do this, you might find a question I asked on one of the static stages about the game theory. So, all right. So no white elephant. You get your gift. That's your done. Centralized economy. It's a planned economy where you're just giving stuff. What do we do with this strategy? It's a greedy strategy. What's the first thing we have to do? What do you do? Huh? You break it. Let's break it. No, you can't break it.
Oh, okay.
That causes a circular self-referential loop of the universe will fall into a black hole. Yes, of course you have to do it for your homework, but right now I want to get another one. Yes?
So say for the first example for the gift.
Okay, so let's draw some. So how many people in gifts do you want? Like 2 or 3 or?
You can have 3.
Okay, so let's do 3. So these are people here. These are gifts, and we'll label them as 1, 2, 3, and A, B, C. Okay, go.
So if you look at the gifts first and choose the max value to decide which person, say for gift A, person 3 values that the most.
Do you need a number? It doesn't matter.
Sure, they value it at 2.
They value it at 2, okay? And everyone else has a lesser value. Say,
And 1 and 2 value it at 1.
1. Okay, good. Thank you. Oh, that was a mistake. Okay. So 2, 1, 1. Okay. Okay, good.
And then for gift B, person 3 values it at 10.
Let me use it. Okay.
And then 2 and 1 could be any number.
Any number?
No.
5,663?
They can also be 1.
Okay.
Again.
You should know better than look better. All right. So you claim this is a counterexample. Why is this a counterexample?
Because person 3.
So let's say what the greedy solution will be. The greedy solution will take gift 1 and assign it to person 3.
Yeah.
Then it'll take gift 2 and assign it to person either 1 or 2.
Yeah.
We're not worrying about gift 3 right now, but that's okay. And the total value we're going to get is 2 plus 1, which is 3. Whereas the optimal strategy would have been to assign gift 2 to person 3, and then maybe gift 1 to person 2, and you'd get a value of 11.
Yeah.
Okay? Okay, good. So we can agree that this greedy strategy will fail, and I will let you entertain yourself by figuring out if there's any greedy strategy that can work. I'll let you think about that for a bit. But that's not what I want to do right now.
How do you get, what do you say, you get a value of 11?
I get a value of 11 if I assign gift B to person 3, and gift A to person 2, and person 1 has to wait because we've got more gifts coming. So it's not a full example, but you can imagine that, okay, for the rest of the stuff, everything works fine, but now just with these So in fact, really, the problem is just with these two. You could redo the example of just 2 things here and 2 things here, and that would be enough to show the problem, right? So sometimes when you come up with these counterexamples, okay, we have the stuff, but then you can, okay, let's rewrite the example by removing 1 and removing 3. So now we have a 2 and 2, and this all these edges, just that's all you need, and it will work. You have a 2 and a 1, and you have a 10 and a 1. Okay? And remember that because people and gifts are in some sense symmetric, and a counterexample for the first version of the strategy is also a counterexample for the second version of the strategy. You just flip everything around. So you can, they work either way. So like I said, you can think about whether there is in fact a greedy strategy that would work for this. Of course, we don't know ahead of time if there is one or not. There might be. This one doesn't seem to work. But what I want to talk about is a way in which you could try to modify this to make it actually work. In a way that is guaranteed to be close to the best answer, while not being the best answer. And the trick I'm going to do, so the idea of local search, like I said, is to look at your solution and make local improvements. So here's an idea for a local improvement. You take 2 people. So I don't know if you've, so you take 2 people, and you look at the gifts they got. Okay. Suppose it turns out that for those 2 people, swapping their gifts would have made the overall value better. So either one person is slightly less happy, but the person's really happy, or both of them get a little bit happier, or something like along those lines. Right? We swap it. So let me write this down. So the local operation we're going to perform, and remember this can only be defined once we have a solution to begin with. So I'm saying is look at the solution you currently have and tweak it. And the tweak is, so tweak the solution for, so if there exists a pair I comma j, okay, such that, and I'm going to write this in sort of notation just because it's more concise, vi pi I, which is the current value for what I'm getting from I, plus bj comma pi j. Okay, this is the current value of what the solution is giving. So these 2 people is less than, what would I be? It would be, what would I be writing now?
Vi pi j
Plus
bj pi I.
Very good, because I swapped them around. If that's the case, then swap the assignments of I. This is what we call a local improvement. So it's an improvement step because we're trying to make the solution look better. It's local because I'm only looking at 2 things. I'm only looking at 2 and trying to swap them. You could imagine, well, what happens if you have like a network of 3 people? You kind of did a cycle swap among them. That might be even better. It's like, sure, I'm not going to care. I'm only worried about 2. Okay, that's okay. It's a local search. It's almost, I'm saying, okay, I'm willing to look nearby, but not too far. And I keep doing this as long as I can find a pair. So this is going to take some time. So we're not right now worried about time, but you can imagine if I have to look over every possible pair, it's going to cost me some time to do this. Notice that I will never come back to a pair So I would like to say this procedure stops. What I first wanted to say was I will examine every pair exactly once. You're all nodding at me, but I don't think that's true. Could I come back to a pair a second time around? So I find a pair. Oh, they're coveting each other's gifts. I swap them. I go to smaller stuff. Could I come back to them and have to do it again?
Yes.
You could, right? Because one of them could get swapped. One of them could get swapped. So, oh wait, now again you have this problem. So my first attempt to prove that this problem converges, I want to say, look, I encounter every pair exactly once. There are n choose 2 pairs. This will terminate in n choose 2 time. Right? Forgetting the time to search for the pair. Just number of iterations is only so much. That has failed. So now what can I say? Well, I can say that every operation increases the value. Right? Let us assume for now that all of these are integers. So I can be sure that if I keep doing this enough times, at some point I will stop because either I will get the optimal solution or I will be unable to go any further. Right? There will be no pair I can swap to get anything else. So eventually, in a step that is bounded by the total weights and all the things, I will stop. It's not a great analysis, but I can say something. Yes.
So you said either you achieve the optimal solution or you can't swap any more pairs.
Right.
Why?
Because each pair, they all like what they have.
But that should be optimal.
Sure.
I mean, I don't know.
Is it? Good. It's a good question. Is it possible that if you do this operation over and over again, and you get to a point where every pair of vertices are happy with what they have, then you have in fact reached the optimal solution? That's a valid question. That's an algorithm. What do we do with algorithms? We break them. Some of them example. To come up with an example to break this, you're going to need at least 3 things.
So,
Where every pairwise thing works, but there's a 3-way swap you could have done.
yeah.
Well, yes, it has to exist. I don't know if such a thing exists. But that's what, if such a counterexample existed, that's what it would look like. You'd have to have 3 things. Any thoughts? I'll give you maybe a minute or something. You want a suggestion? Or you
Well, yeah, I was just thinking that the pair that needs to swap can't be located because another pair needs to swap.
I don't follow.
So
remember, no pair needs to swap. That's the property
I know,
of
but
this.
like,
Yeah.
what would be a better solution can't be found because I don't know how to explain what it.
I think what you're saying is you're saying that there should be a way to get stuck where I can't make any progress, but there is somewhere better to be.
Yeah.
And what I'm saying is the way in which that could happen is if there were 3 edges. Pair-wise, they all looked okay, but if you look back and said, okay, if the 3 of you could talk to each other, you could actually get a better answer. That's what. So I don't know what that looks like, but we have to think about that. How would you construct such an example? So I'm giving you a meta answer. I'm saying if you wanted to find an answer, that's what it would have to look like. But or more. Maybe 3 is not enough. I don't know. But I think 3 is enough actually. But can you come up with an example of 3 things where every pair works fine, but now over all 3 you could actually do something different? And maybe you can't. Maybe it is all. I'm not saying it. The questions you're asking, the questions we're talking about right now, are very important questions that go to the heart of how you think about local search. So I'm glad you're asking these questions right now.
Okay,
You have an example?
maybe.
Okay, sounds good. So how many things do I need?
4.
Need 4 things? Okay, let me draw. 1, 2, 4. 2, 4. These are people. These are gifts. Okay.
Okay, we'll see if this works.
See if this works.
So person 1 has values for A, B, C, and D of 4, 3, 2, 1. Person 2 has.
You know what? I'm going to do this like a matrix here. It might be easier. Okay?
Okay.
Go ahead.
Person 2 has values. Sorry, this was complicated, so.
Yep, that's fine. Take your time.
4, 3, 2, 1.
Also, the same as before?
Yeah.
Okay. Yep.
Person 3. Let's do 1, 4, 3, 2.
Okay.
And person 4. 1, 1, 4, 3.
1, 1, 4.
Yeah.
Okay.
I'm making things up, so
Yep,
we'll
that's
see.
fine. That's fine, and that's a good way to start.
Okay.
Pick things up, and then we can tweak things as we go along. So.
Okay.
Okay. So, what is the best local solution?
So if we start with person 1 and give them their best gift.
Okay. So you start with 1 to A, right? Then 2 gets B, right?
Yep.
Okay. 2 gets B. 3 gets C. And 4 gets D.
Yeah.
Do we all agree on that? Okay, that's our first grade solution. Now we do local optimals. So let's look at 1 and 2. 1 has 4, 2 has 3. Is there a way to swap them? No. You get the same cost. We don't swap them. 2 and 3. 2 has a cost. So the total cost here is 2. So this is cost 3. And this is cost 3. If you swap their things, you get 4 and 2. No difference. So you don't do anything there, right? 3 and 4, 4 is the cost of 3, so they both have cost 3. If you swap them, you get 4 and 2. Again, no difference there, right? Yes? You agree? Okay. What about 1 and 3? What happens to 1 and 3? Now 1 and 3, their current cost is 7. If you swap them, you get 3, which is terrible. So you definitely won't do that. Okay. 1 and 4, if you swap them, it'll be terrible. And that 4 and 3 becomes so the way I'm doing it this quickly, maybe it's a bit too quick. Okay,
I didn't think through it this far, so.
Yeah. So this 4 and 3 becomes 1 and 1, right? So that's not good either. So the 1 and 4 is not good. Now we've taken care of 1, 2, 2, 3, 3, 4. We've taken care of 1, 3, and 3, 4. Now we have to check 2, 4. 2, 4, right? Okay, so 2 and 4. So that's B and D. You swap them, you get 1 and 1. That's terrible. So I claim this is locally optimal. This is what will happen after you finish the local search procedure. Okay, but this is also optimal. I mean, it's not a counterexample unless this is.
No, it's a counterexample.
But is it? But maybe the solution is optimal.
Oh.
You see?
I was only trying to get the 4s, like.
Well, actually, so currently we have 4, 3, 3, 3, right? This will be suboptimal if I get 2 4s. The way to get 2 4s is to get 1 with A, 3 with B, and then wait.
If 2 has 4.
Yeah, 2 with B has something like 2 or.
Okay, too many people are talking to me. So is someone giving me a solution that's better?
I think
Tell me the solution is better.
if 2's happiness
No, just give me the solution. Just tell me the matching. Don't give me the reason. Just tell me what is one matching to.
Oh, that way, no. I was just telling you a change that could contradict this.
But is it a pairwise change?
Yeah, just 2D. 2D, if they had a happiness value of 4.
No, but you're changing the matrix now.
Yeah, that's right.
Wait, are you changing the matrix to show that the countering that this example is no longer optimal? That's not the goal here. Remember, the goal is to check whether this example is a counterexample to the claim of optimality of the local search. If you're welcome to try another thing, that's different. That's a different game we're playing then. Any other thoughts?
Oh,
Maybe this is optimal by accident and we're in trouble.
also,
Yeah.
what you're asking for is a solution which is greater than what we're given. Right?
Yeah,
So
yeah.
So
I'll need another 4 somewhere because
Yeah.
the max.
if
I need to get 2 4s somehow.
3 is B.
If 3 gets B, so 1 gets A, 3 gets B,
Yeah, then 2.
but 2 can't get either 4 or 3, so now it's in big trouble.
If 4 gets C and 2 gets B,
Okay, so 4 gets C. Yeah.
2 gets,
B. Okay, so far so good.
You get 1.
oh, no, sorry.
But now 3 will get 1 or 2. So my suspicion is that because there's a lot of slack here, we could probably change the numbers to make this example work to have an optimal solution that's not locally optimal. But right now I don't know how to do it. So this is not yet a counterexample. But I feel like there's room for maneuvering here because in some of those cases the swap was so bad that it was clearly not possible. I could increase these numbers to still make the swap bad. So this would still say locally optimal, but the numbers would get big enough that I might be able to play some games here. Right? So I don't know yet. So you should think about this. But it was a good question to ask, right? To ask whether maybe in fact the locally optimal thing is fully optimal. Okay. So I'll let you think about this for a bit. Okay. But what I do want to show, so what I have done is failed to show that this is bad, which is not the same thing as showing that it's good. I have merely failed to show that it's bad. Okay. I would like to say that it's good, but I'm going to give you a sort of a somewhat more weaker statement about its goodness. I'm going to prove to you that it's decent. Seems like a lot of work, but sometimes that's all you can do. Specifically, what I'm going to show you is this. That if you do the greedy whatever, it doesn't really matter what you start with, if it is local threshold, the solution you get has at least half the value of the optimal solution. I like that word. Whoa. Yeah, that is the appropriate response to the statement. Also disbelieving, like, well, yeah, I don't believe you, so that's also a good response. So again, the claim is going to be, and I'm going to write this down, the claim, the result of local search has value greater than equal to the opt value divided by 2. Now, remember, the opt value is the biggest you can get. I'm saying this is more than opt divided by 2. So it's not optimal, but it's not that bad. It's within 50% of opt. Right? It's not 0, it's not 1, it's not 2, it's like, it's reasonably good. Okay? Now we can debate over whether being half of optimal is good or not, but the point is, I'm able to say that it's reasonably close. That's the interesting point, that I can actually say these things. Okay? So some things that, in fact, a lot of people go through entire CS curriculum, undergrad and grad school, they don't realize that you can make such strong statements. And that's sort of, if you think of me as a sort of a practicing person who does algorithms, this is my bread and butter. I use this kind of stuff all the time. It's a natural thing. I almost don't even think about exact solutions anymore. I always think about approximation because for many problems, all you know. So the question now is, how do we prove this? In the past, we've been able to reason that we are optimal by saying, oh, we'll just change opt and the cost doesn't change too much. You can't quite do that here. You need a slightly different way of reasoning, but you still have to imagine what the optimal solution is. Okay. And we're going to use the fact that locally you can't improve. Okay, so the intuition behind this is that someone would want to say that if I can't locally improve by just doing a small steps nearby where I am, then I can't be that bad. Okay? Like if I'm locally in a good place, then I'm close enough to the point. That doesn't always hold, but we're going to show that it holds. Okay, all right. So in order to reason about this, we need to construct the optimal solution, this imaginary optimal solution that we don't actually have. So we'll just imagine it. And let's say the optimal solution is defined by a different permutation. Right? So let's say the op solution is defined, because remember, the output of any procedure is a permutation, an assignment, right? By some permutation. Let's call it Q, from 1 to n to 1 to n. Right? So in other words, in the optimal solution, the person I is mapped to the gift Q of I. Okay? Yeah? And remember the local search property that we have? That for every pair of people, we know that the opposite of this is true. That this is greater than or equal to that. Swapping does not help. Because that's where we stopped. So we're going to use that property. So far so good? Okay. So what's the plan? Here's the plan. We're going to try and imagine the optimal solution in juxtaposition with our solution. In other words, we have some kind of assignment. So we have people, and we have gifts, and we have some assignment, right? So I'm going to draw assignments in blue. Maybe I should do it in red because we're Utah. Well, no, we're blue and we white. Never mind. I just confused myself. So let's say the solution the algorithm is providing is the blue one, which is inferior. Oh yeah, this is being recorded. Never mind. Okay. And the optimal solution, which we will mark in red, looks slightly different. Maybe some of them are the same, but maybe some are different. So I'm just imagining. So let's fix one particular element. We'll call this element I. Okay. Now in the algorithm solution, this maps to pi of I, right? In the optimal solution, it matches to Q of I, right? And in our solution, the blue solution, Q of I was matched to some other unknown element J. So again, we're doing a little walk. What we're saying is, we had our solution, opt chose to match it somewhere else, but that got matched to someone in our solution as well. So now we have I, and we've defined now J by this process. So you take I, you walk up the optimal, you come back down on yours. Okay? Yeah? All right. So let me set this up carefully here. We're going to play some games here. I want to write down some function that describes the cost of my algorithm and compare it to the optimal solution. And I want to say, okay, this is greater than equal to optimized by 3. Right? I want to say that. So let me write down an expression involving mine. So I'm going to add up all the blue edges, which is the cost of the algorithm, right? And I can write this as, so the algorithm cost is equal to sum over I, V of I, comma, I. Is that right? Yes? Okay. But suppose I summed it up in a different way. I said, okay, rather than summing up all the blue edges in the usual way, for each I go do this weird thing and find J and sum up all the JQIs. So my notation is a little sloppy here because it's not clear what I is, but imagine that this procedure is what generated J, and I'm summing it up this way. I'm summing up the same edges I'm just indexing it differently. Do you see that? Right, I'm still summing up every single blue edge, but every single blue edge can be written in terms of this path through opt versus just directly through I. So I assert that this sum is in fact the algorithm cost as well. I'm just summing up the same blue edges, but in a different order. You see, right? I mean, this might seem a little silly and pointless, so bear with me for a minute, but do you at least agree that these two equations are correct? The first one is, yes, by definition, but the second one. Thoughts? Or confusions or questions?
The UI, oh, that's V. That's
V, sorry, V, yeah, V for value. Yeah. Right, I'm just summing up the edges in a different way. So if I put them together, I can say that 2 times the algorithm cost is equal to sum over I of Vi, comma pi I plus Vj, comma Qj. Okay? Where Qi, sorry. I got myself mixed up. Okay? Okay. Now, remember, these 2 terms refer to 2 different edges in the solution provided by the algorithm. Right? They're both blue edges. If I were to swap their assignments, what do I know for sure would happen? Sorry? Will increase or decrease? Because remember, I have said that my algorithm is what I get after, my solution is what I got after running the local opt improvement. So I have made sure that for any pair, swapping does not help. So if I swap this, the values, well, will be more precise, will not increase. It might stay the same or it will decrease, right? If I were to swap them, what will this look like? So now I can write this as, this is going to be greater than or equal to the sum over I. So I'm going to swap them. So it would be V of I, comma Qi plus V J, comma pi I. Is that right? Yeah, that's what happened when I swapped. It's like I took those 2 edges and I swapped them. I got that and that. But notice what just happened here. Let us look very closely at this term. What is this term? This is the value that optimal assigned to I. Right? In fact, if you see the picture, look at the 2 blue and the red. If I swap the assignments, one of them is going to be that red edge. And there's going to be some other edge there, which is the other term there. Right? Okay. So if I sum over all I, the value of I to Qi, what is that? That's optimal, isn't it? So then this I can say yes? Since all the values are positive, I didn't say that, but I implied it. Voila. Yes?
I still don't understand the J index here. Is that
Okay,
fixed
yeah.
index?
Yeah. Good.
So
No. It's not, that's what makes it a little sloppy. But let me try to be more clear about this. You should think of J as something derived from I. And the way we derive J from I is, you look at I, you look at where the optimal solution sends I, and then you look at where the algorithm what the algorithm would have sent to that thing. So think of going from I, taking a red edge up to Qi, and taking a blue edge back to J. That's the way in which J is produced. So whenever I say J here, it's the J coming from that I.
But we don't know the optimal solution yet.
I don't. I agree. I do not know the optimal solution. I'm just writing equations here, right?
So J is undefined because I don't know.
Yes, it is undefined. I can't produce J for you. I agree with you. This is a weird thing about reasoning about optimality. I am not saying that I know J. I do not know J. All I'm saying is, whatever it was, this equation has to be true. Whatever J was, this equation is true, and then this, and therefore the whole thing. This is the totally bizarre and counterintuitive things about this reasoning. I do not know what optimal is. All I know is it must have certain properties. It must be a matching, right? I must have such an edge. Whatever that was, it must be something. So I must be able to write this down. If someone were to give me opt, I should be able to write this down. Right? It does exist. I just don't know what it is. And this inequality holds because of the property of the algorithm. This property is just by observation, because it's just algebra. And then finally, you get that. All of this is algebra. It's algebra imagining what the optimal solution is doing. Just like we did for our greedy analysis, we said, okay, imagine what opt is. If opt doesn't have this property, then I can change it and do something with it to make it look like greedy. I didn't know what opt was. I just said, look, if there was such a solution and it didn't have this property, I could change it and make it look like it has a property without affecting its cost. I can keep doing this, so now my greedy is optimal. We did the same kind of reasoning there, but I just kind of slipped it by you all. So he's like, okay, this makes sense. But now you're saying, okay, I really have to reason about opt without knowing what it is. But all of these equations are correct. I don't have to actually know J to say that this is true. I don't have to know J to say that this is true, or this is true, or this is true, or that this is true. Another more intuitive way of thinking about this. There's another way to think about it. I'll get to your question in a second. Another way to think about this is to say this. If you look at this picture, our solution has these two blue edges there, right? And there's this unknown red one in between. Right? In fact, the blue edge is defined by this unknown red. Okay. What you're saying is that because we know we can't swap to improve, because we've already made sure all pairwise swaps are good, or all pairwise swaps that could improve us have been made, we know that the swapping is going to reduce our cost. Okay? And if the swap is going to reduce our cost, and one of the edges is the optimal solution, then that optimal solution has to be, it can't be too big. Otherwise, I would have been able to improve my cost. And that's where this factor 2 is coming from. Maybe this intuition didn't help you. That's the problem with intuition. Sometimes it helps people, sometimes it doesn't. But that's another way to think about what this algebra is doing. Because we don't start by thinking about the algebra. You start by thinking about, okay, what would happen if you swap? Okay, write down some equation, then you end up with this, right? But yes, there was a question there. So why do you all ponder this? Why take the question?
We have just like have a lower bound right now. Can we have something like, okay, I started with some and I may reach the optimal also if I start.
So this does not preclude me from reaching optimal. It's saying that I'm never too bad. I'm always between opt and opt over 2. It may be that I'm optimal as well. That's fine. But I'm at least this much good. Right? So no matter how pessimistic the situation is, I'm at least going to be half. Right? But I could be much better. So we've got about 5 minutes left, so I'm just going to stop while you just think, and then maybe questions will come. Yes?
I was thinking, so essentially what we're trying to do is exploit the properties of the algorithm and then express it algebraically?
Yeah, sort of. I mean, at that level, yes, that's what we're at.
Okay, so what would be a good technique then to go from expressing the property to algebraically? Because
there's no standard technique.
No,
we're already in uncharted territory. I mean, so the time in the algorithms class where everything is nice and regular and sort of is organized, we're just about to leave it. Today is the day when we move away from dynamic, greedy, divide and conquer to things which are a little bit more fluid. There will still be structure. When you get to randomness, there'll be standard techniques you can apply. But there is a certain amount of creativity that's going to come into the design process. And I think one way to think about this is to, I don't know. I mean, I could babble on for a while as to how you should think about this, but that just works for me. Yeah. Right? These things are not they're not hard and fast rules. the overall trick with things like this is to try and say that, okay, so when you're doing approximations of this kind, you're generally saying something like this. You're saying, in this case, my optimal solution is up here. My algorithm is somewhere. I don't know where it is. I need to prove it. What I want to show is that even though I can't reason about what the algorithm is doing and what Opta is doing, there is some other quantity here. We'll call it L. And I can reason about two things. That number one, L is close to opt, and two, algorithm is close to L. And usually L is some proxy for optimal that's a bit easier to work with. And in some sense, what we're doing here is saying, because of the local search procedure, and because we're guaranteed that local swaps cannot improve the cost, we're basically saying that these two edges give us a handle on what this value is going to look like. Because there was no reason to swap this to give me that. That means this isn't that good. This isn't that big, which means these aren't that small. Right? If this was a really good value, I should have been able to swap to get a better answer. But I didn't. So it's not very good. That's sort of the idea. And then the rest of it, yeah, like I said, it looks like elementary algebra, but it's sort of weird. It's like it just seemed like magical. This all just happened. Maybe that's the feeling you're getting. Yes.
When we're talking about the paths for the approximation, so we start at person I and then travel up the greedy local search.
The blue one, yeah, to pi I.
It's pi I.
But actually, so you don't actually have to travel. You start from I, you travel up the optimal solution to qi, and then you go backwards to j along the algorithm.
Okay.
Right. And if you think of this three-edge path there are two blue things and one red thing. And I'm saying, suppose I swapped it to get that and that instead. And we're saying that swap is not going to help you because of the guarantees of algorithm. So if it's not going to help you, this can't be that good.
QI is our optimal solution, right?
QI is the optimal solution. Yeah. I mean, what we're basically saying is that, look, at least we can say that this plus this is more than that. Now that's not good, right? Because we're basically using two of our edges to account for one optimal edge. But it's just two. That's where the half comes from. We're saying that we can say that two of our edges, any two, are equivalent or better to one optimal edge. Right? That's the key. If we can say that two of our edges are as good as one optimal edge, then overall our cost has to be about half of optimal. Because we take two edges, you get one. You take two, you get one. You get two, you get one. So you've got about half of that. That's the idea here, right? Because we know that this optimal isn't that great. If this optimal was huge, then we couldn't have said that these two together could not have been as good as opt. But if it was huge, we could have swapped, and we didn't for some reason. So it can't be that good. That's the idea. Okay. Because swapping is not possible, that edge you could have chosen is not that great. It's at best, it's at worst case, the sum of our two edges. And that's fine. That's okay. That means we've got half. Yeah.
Just to be sure, this algorithm is greater than or equal to optimal by 2. It's just for this case, right?
What do you mean this case? It's for the whole thing. We're looking at, remember, we're looking at the total cost of the solution produced by the greedy local search procedure.
No,
right?
in the sense of this problem of assigning a people with kids.
Yes, for that problem.
Only for that problem
Yes.
is optimal by 2.
Yes.
Yeah.
There are many problems for which you can't even get that. It's optimal divided by log n. There's some problems for which you can't even do that.
Okay.
It's basically optimal divided by n or close to that. It's really terrible. So there's a whole spectrum of problems that have different behaviors with respect to what you can approximate. So actually I didn't tell you this, but you can actually also show that there are problems for which you actually can't get within 2. So there's negative results that you can't get as optimal, Then there are positive results that you can get within 2. Then the negative results say, well, even for some other problem, you can't even get within 2. So there's a whole spectrum of things you can say that gives you a different lens on the hardness of problems based on how well you can approximate them. And we'll talk about more of that. Okay, I'll take one last question because we're out of time. So if you want to come to an office, or if you can talk about that. Yeah.
So like for an arbitrary problem, you just keep doing it and trials until you find a way to prove. Like you start with 3 by 4 of optimal, you start with opt by 2, and then you keep on doing these guesses.
I was going to say welcome to my life, but no. But it's not as blind as that. Because after a while, after you study enough of these techniques, you start realizing certain techniques only get you so far. And if you want to get beyond, you need a brand new technique. And then someone will show that that class of techniques cannot get you any further, so you need a whole new one. So you'll start with this kind of thing, okay, this breaks, you'll say, okay, we'll write a linear program and around it, okay, that breaks. Okay, you'll do a semi-definite program and around that, okay, that breaks. Then you have these higher order programs that are, there are all kinds of things. So it's not totally blind. You just have, okay, my toolkit can get me so far, and I know that. And I need another toolkit that gets me so far, another toolkit, and then keep trying. And that's what we try to learn a little bit of these things, the toolkit. Okay, so I'll see you all on Friday. And I'll check the notes.